Hi everyone, I'm Bo Yugao from Jinan University. I'm really glad to share our work, which focuses on evaluation of body-centric locomotion with different transfer functions in VR. Thanks for our co-authors for this work. The contents of the presentation include the following six parts, so let me introduce them. The body-centric locomotion allows users to naturally navigate virtual environment with body parts, for example head tilt, arm swing, or torso lean, as the figure shown. The major advantage of such a method are that users can navigate with body parts in a small space, even without carrying or holding extra input device, also supporting concurrent interaction tasks. For example, navigating while selecting targets. The transfer functions are required and important for those techniques to translate users' physical actions into the virtual movements. The example of head tilting shown. The variety of transfer functions could enrich body-based locomotion forms in VR, but it also poses challenges to locomotion design in three aspects. First, it's unclear what mapping functions could be suitable. Secondly, it's ignored the difference of multiple control properties. Third, it lacks a comprehensive understanding of user preference in body-centric locomotion with different transfer functions. So we connect the related work based on transfer function types, body parts, and mapping mechanisms. We connect the linear function, power function, and piecewise functions, and also we connect the head, we connect the head, arm, torso, and the knee body parts. So in summary, there is no generalized and controlled research to look into the performance of body-centric locomotion techniques with different transfer functions in VR. So in this work, we utilize the within subjects experiment design to investigate this issue. We recruited 16 participants from the local campus. We utilize the HTC Vive Pro device. And we select four body parts and four transfer functions from the summary of related works, which mentioned before. And we evaluate the performance with objective and subjective measures. The task procedure included three phrases. It's practice phrase, formal test phrase, and question phrase. As the figure shown, the formal test phrase, the participant will asked to navigate to the target position as quickly and accurately as possible. In total, there were 4,608 trials across 16 participants. For the experiment results, there were no significant main effect for body parts on task completion time, while transfer functions and the target distance had a significant main effect. CL was fast, while CP was the slowest. A task time increased as the target distance increased. Also, induction effects was found. And for the rate of failed trials, a significant difference of body parts and transfer functions were found. The head had the lowest rate, while torso led to high rate, probably due to the tightness caused by leaning torso while standing during experiment process. And CL function result in highest rate, and then other three functions due to it was too fast to control when approaching the targets. And final position offset, there was no significant effect for body parts and for transfer functions. As expected, large target distance made it easy to result in large position offset, and low induction effect was found. For the subjective questionnaire, body parts did not differ, while transfer functions had a significant main effect. L was rated highest score, while CP had the lowest score. And for the discussion of the result, thanks to easily and control the body parts in a sample navigation path, then the locomotion performance did not vary across body parts in task time, position offset, but varied in rate of failed trails. Head was rated as the highest score, while torso has the slowest score. However, locomotion performance depends on transfer functions which are used. The linear function was the most preferable, while CP was rated as unsuitable due to its slowest speed. We also analyzed the result between the accuracy and the efficiency from the result. And we regard the head and the L and the CL function as the highest priority, and followed by arm and the knee with the L function. We also propose the implication design. Um, for example, users can navigate using body-centric locomotion master in a forest virtual forest sense. We also point out the three limitations, including navigation directions, seamless reaching between different body locomotion masks, and setting posture. To conclude, we systematically investigate these body parts and transfer functions on virtual locomotion, and we analyze the experiment data, provide the design implementation, and also we pro, pro, and also the result could provide preliminary suggestions for designing future body-centric locomotion in VR. Thank you. Please read our paper for more details.